Okay, good morning or good afternoon, everyone. I see it's straight up 10 o'clock here on the West Coast, and we're going to be starting our webinar in just a minute. So I wanted to welcome everyone to the Composting Collaborative's December webinar. I am Kerry Oceans with the U.S. Composting Council. We're one of the founding members of the Composting Collaborative. The collaborative is an initiative that Green Blue, Biocycle, and us, the USCC, founded almost 2 years ago. The mission of the collaborative is to unite compost manufacturers, consumer-facing businesses, and key stakeholders and policymakers to share best practices and resources, as well as generate innovative solutions to share challenges. Since we kicked off not quite 2 years ago, we've grown to around 90 members and over 2,000 subscribers. Our monthly webinar series, which you're about to participate in, is one of the ways we aim to highlight best practices and case studies. We're waiting just another minute to allow additional participants to log on, so we'll be getting started shortly. Now, we currently have everyone's phone line muted to ensure good audio quality. Throughout the presentation, though, please feel free to ask questions using the chat box on your ReadyTalk control screen. We will try to answer as many questions as we can during the Q&A portion at the end of today's webinar. We'll also be recording today's webinar and slide deck from today and making that available. Here's happy to have everyone join. Make sure everyone is in the right place. This is the Composting Collaborative webinar, as I mentioned, our founding partners and our over 90 members. And this is just some of their many logos. If you're interested in joining as a member, you can take a look at our website and reach out to us. So I am particularly excited to get started with today's webinar on per and polyfluoroalkyl substances, PFAs. PFAs are a group of man-made chemicals that have been manufactured since the 1940s. They're used in a variety of industries. They've been used as stain repellents on fabrics, grease barriers, in food packaging, and our famous Teflon of the title. However, good evidence has emerged that exposure to some PFAs can lead to adverse human health effects, and while the use of certain PFAs has been phased out or is being phased out, many are actively used and can still end up in our compost. So I'm particularly excited to hear today's speakers. If you are like me, you've been vaguely aware of this growing issue, but you haven't had the time to really dig into it. However, the U.S. Composting Council has been asked to sign on to several letters regarding this issue over the last month. So I figured it was time for some self-education. And since my role at the USCC is to work with the Composting Collaborative and do these monthly webinars, I figured it was a great opportunity to invite all of you who might be in a similar state of knowledge to join me. So today we'll be hearing from 4 speakers exploring different aspects of this issue. Their longer bios are on the webinar website, so I'm just going to briefly introduce them here so we have more time to hear them. First, we'll hear from Ned Beecher, Executive Director of the Northeast Biosolids and Residuals Association, NEBRA. He has led efforts in the biosolids profession to understand PFAS related to biosolids and other residuals. He was really instrumental in helping to put this webinar together and give us the basics of these compounds and the threats they bring. Ned will hand it off to Jeff Cooter, CEO of AgriSource Incorporated, a Massachusetts company engaged in composting and the sale and distribution of compost in the Northeast. He's got more than 30 years experience in the design and operations of facilities using a variety of residuals, and author of more than 35 scientific and technical papers. And Jeff will focus on how these issues the PFAS, impact compost manufacturers. After Ned, we'll hear from Rooney Kim Lazcano, a doctoral candidate in the Ecological Services and Engineering Interdisciplinary Program at Purdue University. And her research is relevant as it focuses on the environmental fate of PFAS and other pharmaceutical and personal care products in waste-derived fertilizers. Finally, or not finally, penultimately, Rooney will introduce Rhodes Yepsen, Executive Director of the Biodegradable Products Institute. Rhodes will let us know what the compostable packaging community is doing to reduce and eliminate PFAS. And finally, we'll head back to Ned for a wrap-up of the webinar with some recommendations for compost manufacturers in the light of what we know and what we don't. So we're in set up for a fantastic set of presentations. If you've just joined us, reminder that we're recording today's webinar, and those will be distributed afterwards. We'll also have everyone's lines muted, but please do ask questions. And with that, put your thinking caps on, and Ned, I'll turn it over to you.
Thank you very much. I'm hoping that you can hear me now.
Very much. Thank you.
Thank you, Carrie. So I'm going to introduce the topic of PFAS and some background information that will be useful in advance of Jeff's, Rooney's, and Rhodes' presentations. So PFAS are, as Carrie said, per and polyfluorinated alkyl substances. They are defined as chemistry that has a carbon backbone with fluorine attached either to all of the carbons for perfluorinated compounds or some of the carbons for polyfluorinated. And they have a functional group on the end which defines the particular chemistry and the uses and properties of each compound. There are about 3,000 or more identified, some as byproducts of manufacturing process and such. These two that are shown here in the yellow are perfluorooctanoic acid, the 8-chain version of the acid PFOA, and the other 8-chain version that's common is the fluorooctane sulfonic acid PFOS. And these two have been mostly phased out of use in North America, but they are manufactured elsewhere, and we still find them some in products, and because they're persistent, they are of continuing concern. There are other PFAS that have been introduced as that are substitutes for those, and their chemistries and the details on them are not as well known. They haven't been researched quite as much, but it complicates the situation. The basics on what they're used for and how or their particular properties include that they can be water soluble and they are hydrophobic, lipophobic, and they bind to proteins. They tend to be very persistent, as I mentioned, especially the longer chain versions, and some of the shorter ones will remain in the environment for many years. There is no known natural breakdown process for them, which is why they are of significant concern. They tend not to be volatile. They can get into the environment through air deposition from manufacturing facilities. They can leach to groundwater. They can affect surface water. They are found widely throughout the environment in many different places, including in the Arctic and in various organisms. Human exposure is considered to be greatest right now through drinking water as well as through food and food packaging, perhaps indoor dust and product exposure. These chemicals are in our daily lives. They've been around since the 1940s and 50s, and so they are very common in our modern environments. There are quite a number of differences between the different chemicals, though they share some common chemistry and properties. It's hard to lump them all together and say that they're all have one particular or several particular kinds of impacts or fates and transports in the environment. As I mentioned, there are no natural counterparts. There's a great deal of information available about how they are used in what industries and such from the Floral Council website. Leave it to say that they're used widely in manufacturing and in various industries, so exposures are clearly can be significant in those locations perhaps. Firefighting foams have been a major source of release to the environment, as we'll look at here. The largest sources really that seem to be appearing in the big picture as states and governments look at where PFAS are found in the environment tend to be around manufacturing sites. Like this is the Parkersburg, West Virginia manufacturing facility of DuPont Chemours that manufactured PFOA, and so impacts to drinking water and other environments around that facility were significant. Also, Cottage Grove, Minnesota area, where 3M and others manufacturing facility also. So those are the kinds of significant hotspots, I guess, that we have around the country or around industrial facilities where the chemicals are produced or used in high volumes. The other sort of major source that has led to impacts on the environment are firefighting situations where either practice firefighting or real firefighting goes on using AFFF foam that is used to put out fuel fires in particular. The white material in these photos is showing the foam being sprayed on a tanker, jet fuel tanker plane at Pease Air Force Base in New Hampshire. So large releases of PFAS chemical in these historic firefighting situations. So those lead to major releases, but there are then minor releases perhaps to the environment through other pathways, and there are many other pathways to the environment, but because of amount of time we have, we'll focus, in our interest area, we'll focus on the fact that compost digestates, biosolids, and residuals, they all mirror modern life if we are using feedstocks from society in their production. So we know this now, even though these have been around for decades in our materials, we know about it now because of the advances in analytical chemistry. That's sort of the basic background I'll give, and I'll then point you to these useful resources from the Interstate Technology Regulatory Council. These seem to be a good place to learn a lot about PFAS quickly, and it's good, accurate information. So I urge you to look at those documents for further background. And also, in terms of our particular perspective here at NEBRA and concerns about the potential for impacts to residuals recycling programs, composting programs, biosolids management programs, we have this two-page fact sheet available on our website. So what is the level of health risk? There is debate. That's not ours to figure out, but we are commenting and tracking that so as to help perhaps avoid a rush to judgment without full science. Sources of exposure, the slide from EPA, are, as I said, drinking water is a major concern these days. And there's been quite a bit of study of that and understanding of the fact that by drinking water, our blood levels do rise. There is significant correlation of drinking water with PFAS and having increased levels in our blood. Food is also implicated by some studies. Fish especially seem to bioaccumulate PFOS and some of the other PFAS. Food packaging is a concern we'll learn about later. House dust may be a route of exposure, especially for children, and workplace exposures, of course, are at another level as well. Looking at sort of a summary, as I said, there is debate still. There's a lot of evidence from various reviews of the science by ATSDR, a division of the Centers for Disease Control, CDC, that suggests significant concerns about PFAS health impacts. EPA also did a thorough review of the literature, which is sizable, to set their standard of 70 parts per trillion for drinking water. That's a screening level, advisory level, public health advisory level. But there's also reviews of the science that look at and indicate, that the evidence is not as strong as some believe or have claimed. Cancer study of around certain hotspots in these states, New York, New Hampshire, Minnesota, did not find a correlation with PFAS. So if and when PFAS are causing health effects, they appear to be subtle. Reasons for concern, though, really are that the PFAS in drinking water does elevate PFAS in our blood. These chemicals are persistent in humans. PFOA and PFOS have half-lives of 4 to 7 years in our bodies. So that's cause alone for concern. And then we don't have as much data on the other PFAS as we would like to have. Interestingly, there's been a study by the Australian Health Panel that found very kind of different outcomes, so it just is evidence that there is debate along the health. And one of the things that comes up because of the health concerns and along with standard toxicological processes and risk assessment, uncertainty factors are applied heavily in trying to set levels that are protective of public health. So this diagram from a Michigan DEQ presentation just indicates that the conversions of research data from animal studies to humans and humans to additional protections, et cetera, involve uncertainty factors and conservative protective factors. NRDC, the environmental group, has recommended drinking water numbers for PFOA and PFOS in the 4 to 7 parts per trillion range, which is an order of magnitude lower than EPA's 70 parts per trillion, and that's because they have increased their uncertainty factors applied to their calculations. But as I said, the major concern now is drinking water. Before 2016, PFOA and PFOS, EPA had an initial short-term health advisory that totaled 600 for the two of them combined, actually 200 and 400 separately. But then in May 2016, the sort of modern era of PFAS concern started when EPA created the 70 parts per trillion screening level. It's a public health advisory level. And then that was driven by research around the C8 study and other evidence in the literature. And at that point, many water utilities and well owners began to act in response because more water systems were found to be above or close to that 70 parts per trillion. So here's what states have gone, a typical kind of process states are going through in evaluating PFAS. And this, again, the focus is on drinking water initially, and that being a major exposure route. So human health protection was a major concern, has been the major concern. So water wells, this is the state of New Hampshire, shows how much testing there's been. Thousands of water samples tested, most of them not showing PFAS above 10 parts per trillion. The green ones are 10 parts per trillion or less. Yellow is 10 to 45, and then above that is orange, and then the ones of concern might be those above 70, which are the red, and above 400 are the purple. So it is being found in considerable numbers of wells. And this kind of pattern has played out in other states as well. Then a lot of the black stars on this show remedial sites, so land cleanup sites that are ongoing where the state has required some testing for PFAS as well as the other chemicals being addressed, and so some of those sites are showing, again in purple, the high levels greater than 70 parts per trillion in the groundwater at those sites. So again, looking at remediation sites is sometimes the next step that states take. Then zeroing in a little closer to particular hot spots, there are maybe landfills in this particular situation. There may be firefighting locations, and then there may be industrial facilities that have particular concerns around them and show higher numbers of wells impacted above the 70 parts per trillion. For example, this industrial facility here with drinking water wells around it, many of them in red here, showing greater than 70 and some greater than 400 parts per trillion in drinking water. And those are the sites that states are going after and are addressing appropriately to reduce that human exposure at this point. Part of the system may be to test for blood to see how the communities affected by drinking the water over some time, how their blood levels are and how those compare to the average population. Pretty much all of us, health data show that all of us have some PFAS in our blood, measurable single parts per billion levels. Again, parts per billion compared to the drinking water standard, which is in parts per trillion. So this kind of data is being tracked regularly in most states, many states. And then what happens when we begin to look, states begin to look at other potential sources or conveyors of PFAS chemicals, waste management begins to be considered. And so some states have gone to sites where biosolids or composts with biosolids in them or other residuals like paper mill residuals have been used or managed over time, finding some sort of worst case scenario, high use sites, and they find some impacts in groundwater wells. These numbers are in nanograms per liter or parts per trillion, showing groundwater wells at this site that got up as high as several hundred. This is a long-term biosolids management site that did not have groundwater or drinking water wells anywhere around it that were affected, and but some of groundwater wells under it were affected. And this is another example, my last of this section on state response, where paper mill residuals and yard waste were being composted in compost rows here, and some tests were done on various samples of the materials and of the pond here, for example, showing PFOA at 100 part per trillion in the pond water, and 140 in the PFOS in that pond water, and some windrow leachate, showing higher levels. So again, compare these numbers, these parts per trillion in the water, to the 70 parts per trillion drinking water. And of course, nobody's drinking these waters, so this is not necessarily a problem at this site, but it does raise regulatory concerns. Or some concern for regulators. So that's what has triggered this topic to be of interest to composters and other residuals managers. So looking at the chemistry and fate, here we have an excellent background document by Buck et al. That provides details on this group of chemicals and proper terminology and more. Again, it's a large group. These have been very valuable in commerce, widely used, but their behavior varies in the environment. The interesting thing is that the products themselves, the PFO or the PFAS used intentionally, may also have bring along additional sort of byproduct and similar isomers in their uses. The ionized form, less soluble forms predominate in the environment and in biota. Some may degrade in the environment, but only the longer chains. Eventually, the longer, very long chain versions will ultimately transform to very stable and persistent perfluoroalkyl acids, or PFAAs, such as PFOS and PFOA. It appears that the increasing chain length reduces leachability, so longer chain like PFOA and PFOS tend to absorb some in organic matter and soils and biosolids and composts, but shorter chain tend to leach more easily. If you're looking at the literature for PFAS in soil, we have a site in Decatur, Alabama, where biosolids were applied. Those biosolids had been impacted by an industry discharge that was manufacturing PFAS chemicals discharged into a wastewater facility, and over many years of land application, increased levels were found or caused in the soil at that particular site. It's an unusual case with heavily industry impacted biosolids, but levels did get up, and these are in parts per billion. Again, when we're talking about soils and composts and such, we're talking generally parts per billion. One study at long-term biosolids application sites around Chicago, Illinois, also found somewhat elevated levels in soils, as shown here. A one-time application of biosolids was shown to increase measurable PFOA and PFOS at a typical land application site in Ontario. Looking for comparison at garden control soils in Minnesota, where there was really no direct known impact. Even there, PFOA was measurable, likely perhaps from just dispersed air emissions. And here are some additional numbers of what's been found in soils at sites where there's been aerial deposition and impacts, again, up to 45 parts per billion in the soil. For comparison, it's important to note that the screening level, the lowest we know of, is 300 parts per billion. That's in Vermont. So the numbers in the soil shown previously are quite generally lower, except at that one heavily impacted biosolids land application site. But this is based on dermal and ingestion exposure, so we tend not to be too worried about those with typical biosolids and composts. It's more the leaching potential, and that's what's shown here in this study in Ottawa that shows that when you land apply the biosolids this one time in the tile drainage water, you get up to 23 parts per trillion of PFOA and 3 parts per trillion in shallow groundwater of PFOS. So these chemicals can leach from compost and these materials. And then how they move in the environment is really dependent on the carbon chain length. Again, those with shorter carbon chain lengths tend to leach more, and the organic carbon content. More research is needed to understand the fate of these materials in soils. So here's what we have in terms of the numbers that we know about in terms of regulatory standards or screening levels at this point around North America. Drinking water, the Canadian health guidance is significantly higher than the U.S. EPA guidance at 200 and 600 for PFOA and PFOS respectively. 70 parts per trillion is the EPA standard I've talked about, and that's a good reference point to keep in mind. In Vermont, they've adopted one of the lowest standards with a 20 parts per trillion for drinking water for 5 of the PFAS compounds combined. Soil, again, the 300 parts per billion is based on dermal ingestion and contact, but not on leaching. Alaska is one of the pioneering states trying to set a groundwater leaching protection number for soil cleanup, and these are the numbers they proposed. We believe these are not useful and not appropriate, and the modeling done was not correct, and have commented on that and are glad to share those comments. This literature screening value by Zhao et al. It was proposed for 3 parts per billion, which is pretty typical of that's the range in which composts are, and composts are up to 8 or 10, 15 or more when they have biosolids in them, as we'll see later in this presentation. And New York has this one screening value. So keep these numbers in mind as we proceed with the following presentations. And Jeff, now I turn it over to you. Thank you.
Thank you, Ned, for that introduction. If I can do this correctly. Oops. I've been asked to participate on this as a representative of the composting industry. AgriSource has been making and distributing compost throughout New England for more than 30 years. We work with compost made from biosolids and other residuals, leaf yard wastes, etc. While we're a relatively large player in the market in New England and Northeast, we are probably very small in comparison to facilities and operators in the Midwest and West Coast. Most of the compost in the Northeast and New England goes into the landscape market, relatively little in agriculture, but we also see a very strong demand for use of compost in site remediation, particularly things such as landfill closure and contaminated site restoration work. This has been PFAS has been an issue for a number of years now here in New England, and again, the question is, why should composters care about this? I think as Ned pointed out, the issues with PFAS compounds are considerable. The materials are very widespread. It's not just an issue for biosolids, but we also see PFAS contamination in paper products and packaging, which end up in compost facilities. These compounds are very persistent. They are accumulating in the environment, particularly things like fish. The compounds are readily mobile, readily easily leached, and moving from compost to soil to groundwater as the pathway of concern. In comparison with other emerging contaminants, we are seeing toxicity levels that are relatively high. Thus, regulators are setting very strict limits, as Ned pointed out. Regulators are responding to public concerns and moving very quickly to set limits for both water, drinking water, and soils that are going to impact the use of compost. There appears to be in the regulatory world a race to the bottom to see what state can set the lowest or the most strict limits. As I see it, we are living in the post-Flint, Michigan water crisis era. Regulators are under considerable pressure to take immediate action to protect sources of drinking water from any source of contamination. The PFAS has created a lot of collateral damage. As Ned pointed out, we're seeing contamination of drinking water in both rural and urban areas, or anything in New Hampshire is considered urban, but relatively urban areas. And one of the things that I found recently was this article from Ann Arbor in the press. There were concerns about the use of venison from deer that were drinking, or source of drinking water was from contaminated areas where surface water had levels of PFAS. As Ned pointed out, there are a number of unique properties of these PFAS compounds, and there are also many unknowns. Generally, the PFAS compounds will not break down during the composting process, and you're actually then going to see the potential for concentration in compost over the feedstocks. There's uncertainty as how these compounds bind with organic matter. We know they accumulate, it appears to be in the proteins, animal proteins, but as I see reviewing the literature, it's unclear as how they interact with organic matter. There are long and short chain compounds, and we know these behave in the environment very differently. The long chain compounds are less likely to leach and move through the soil, but they're more likely to bioaccumulate in the food chain. And the long chain compounds are less likely, in comparison to the short chain compounds, to be taken up in plants through the soil. Recently, there was a report put out by the Agency for Toxic Substances and Disease Registry. This report is suggesting that the levels that EPA had established for advisory levels, the EPA established for drinking water at 70 parts per trillion, may need to be ratcheted down to 7 to 10 times lower. Their conclusions, however, were based on minimal risk levels and were not meant to support regulatory action, but are being, unfortunately, used by regulators as the basis for establishing very strict limits in drinking water. And this report also cautiously indicated that PFAS compounds don't appear to show a high incidence of cancer in humans, but there are other, as Ned pointed out, multiple health effects that are much more subtle but of equal or serious concern. So the question for composters, do I have PFAS compounds in my compost? The answer is going to be yes. The real question is, what are the PFAS compounds that are present, and at what concentrations are they? As Ned has pointed out, and as we'll hear from other presenters with significant amount of data, what we're seeing in biosolids compost is the range of 1 to the low tens parts per billion of PFOA and PFOS, as well as other long-chain compounds. But we're also going to see that we have compounds present in compost made with food residuals, where the source appears to be the serviceware and paper packaging. These generally appear to be lower concentrations than the biosolids composts, but perhaps a very different mix of PFAS compounds. The data suggests that leaf and yard waste will have the lowest concentrations of compounds, but this may depend on your particular area and your source. Rooney Kim Lascano will present considerable data on that. Now, for testing for PFAS, we're in a sort of a unusual situation. We still do not have any validated EPA method for soil, sediments, compost, and other residuals. There is a EPA-approved method for drinking water, but no similar method has yet come out of EPA for soils and solids. Thus, when testing for PFAS, different labs are going to use slightly different methods in the laboratory and in sample preparation. You're going to get different interpretations from different labs and different results. So care has to be taken in how the test data is used. In reality, we should be looking at this as for screening purposes only, not as definitive quantitative numbers that are the basis of regulatory action. In testing for PFAS, we are entering also a new world for most composters. Sampling protocol requires the use of field blanks, specialized containers and equipment, and procedures to minimize possible cross-contamination. For example, the recommendations are that the sampler wear washed cotton clothing, not polyester. Do not use waterproof notebooks. No use of aluminum foil or Teflon products. This is a sort of a whole new world for most of us who've been sampling compost, where we're take whatever shovel is locally found, grab a sample, throw it in a Ziploc bag, and send it to the lab. Those procedures are not good enough here. Having equipment that is thoroughly cleaned and where there is no cross-contamination is going to be critical. So if you do collect data, well, what does the data really mean? As Ned has pointed out, we have an EPA advisory for soil based on human contact and ingestion at 500 parts per billion, or about a half a part per million. That's not unusually low or difficult to deal with. Regulators, however, are not concerned with direct soil contact, but rather the impacts of soil on drinking water. In other words, if we have levels in soil below 500 parts per billion, what is the impact going to be on the water, drinking water sources below that soil? EPA has established, as Ned pointed out, a health advisory for drinking water of 70 parts per trillion. Now remember, that's parts per trillion versus parts per billion. And this EPA advisory was based on the combined of two of the compounds, PFOA and PFOS. However, as Ned pointed out, more than a few state agencies are now proposing drinking or groundwater standards that are significantly lower. For example, in Vermont, the established drinking water standard is 20 parts per trillion, of 5 different PFAS compounds. Massachusetts and Connecticut have put forth 70 parts per trillion, but unlike the EPA, again, they're looking at the 5 different PFAS compounds. The question then, if we're really concerned about drinking water and surface water, is will the PFAS leach from composts? The answer is clearly yes. The laboratory tests I've seen using the SPLP method clearly indicate that leachate from compost with relatively low levels of PFAS compounds will very likely exceed drinking water standards. And as Ned pointed out, at one particular compost facility where recycled paper fibers were the primary feedstock, they were seeing levels in retention ponds of up to 240 parts per trillion. Now that was just of those 2, PFOA and PFOS. They looked at more compounds, they would get even higher levels. It's going to be very difficult, in my opinion, to say that is not a problem. However, what we've seen is compost use, sites where compost have been used over time have not been implicated as sites where there's drinking water contamination. As Ned showed in extensive testing in New Hampshire and similar kinds of testing in Vermont, areas where we see elevated drinking water levels are not those areas where we have used compost. Rather, these are sites where there has been use of firefighting foams, for example, airports, Air Force bases in particular, as well as industrial manufacturing sites. However, there are other possible potential sources other than just those industrial and firefighting foams. And more importantly, regulators, as Ned pointed out, are looking at soil screening levels for site cleanup that are very low in compared to that 500 parts per billion. In Maine, for non-agricultural, they're looking at screening levels of 2.5, 5.2 parts per billion, and in Alaska, they were proposing even tighter limits. These soil cleanup recommendation levels are getting very, very close to what might be detectable levels of what labs can readily detect in these kinds of substrates such as compost and soils. So the issue in hand for the compost industry is, can we convince regulators and the public that compost applied to soil is not going to result in exceeding the soil standards and or cause contamination of groundwater, surface water, or drinking water? And will compost be allowed to be used if levels exceed soil cleanup standards? If I have 10 parts per billion of PFOA in my compost, will I be able to use that on a site, a particular remediation site, if the cleanup standard is 1/10 of that or a half of that? That's really a question, and we are seeing in New England cases where regulators have not allowed compost to be used on sites because of concerns about PFAS contamination. As Ned pointed out, there's a lot that we do not know. What are background levels in PFAS in soils and compost feedstocks? What is a, quote, normal level? What are the levels in manures and in other agricultural products and residuals? What of the various PFAS compounds, which specific compounds pose the greatest environmental and human health risks? Most of the health risk study has been based on the 2 compounds, PFOA and PFOS, yet we know that regulators are looking at a group of 5 different compounds when setting regulatory standards. What are the short and long-term potential that when we have PFAS added to soils with the compost, that we will have migration into groundwater? We know these compounds are very persistent. Do they stay in the soil for decades and then show up in our groundwater and surface waters, or they move relatively quickly and readily? And does plant uptake represent a significant pathway? Some of the studies suggest that that is a very minor pathway, but it is of something that I think we're going to see a lot of public concern of if composts are used particularly in agricultural applications. In conclusion, I would recommend that those of us in the compost industry get informed and get involved. It's important that we support research to address some of these very basic questions that impact the safety and use of compost. It's important that we advocate and demand that regulations do not move ahead of the science. Yes, there's public concern, but we shouldn't be motivated strictly out of fear. It's important that we demand that PFAS composts be eliminated from those products that are showing up in our compost as feedstocks. Rhodes Jepsen will talk further about the efforts that BPI are making in this effort. And it's important that we continue to promote the benefits of reuse and recycling of residuals through compost and compost use. We have to advocate for ourselves and for industry and for the proper use of composts and the recycling of organic materials and the benefits they have in promoting environmental health, and not be preoccupied just by the fear that contamination will result in health impacts. At this point, I'd like to turn it over to my next speaker, Rooney Kim Lascano from Purdue University. Go Boilermakers.
Thank you, Bob, for the excellent presentation. I'll be moving into talking about PFAS levels in various kinds of compost and biosolids-based products. I will start with a brief background information on PFAS versus PFAAs, and followed by experiment method and results on PFAA levels in fertilizers, temporal trends of PFAA levels, pore water concentration, which can be related to leachability of PFAS, and PFA precursors that can potentially transform to PFAAs. I will conclude my presentation with a summary of the stock and recommendations for composters. As Ned went over a great introduction to PFAS, I would like to emphasize one aspect on PFAS versus PFAAS. PFAS includes PFAA precursors, which are shown in the PowerPoint slides, and PFAA such as PFOA and PFOS. PFAA precursors can be transformed via biodegradation during composting process and produce PFAA. PFAAs are terminal microbial products which will not be degraded further. PFAA have unique properties that it is much more mobile compared to other organic contaminants such as PCBs. Here's showing one of the pathway from PFA precursors to PFAA to give you an idea of how precursors can transform to PFAAs. One PFA precursors can transform to multiple end products such as PFOA, PFOS, which is 6-carbon short chain, as well as other PFAS. This is also a big challenge for PFAS analysis. Composting of organic wastes is a great way for waste management. However, due to the nature of waste, there are some concerns regarding organic contaminants such as PFAS, which can potentially remain after composting process and can lead to water sources or uptake by plants. To understand the level of PFAA in different types of waste-derived fertilizers, its pore water, which is related to stability, we analyzed 17 PFAS from short chains to long chains in 10 different composted city waste and 18 different commercially available fertilizer, which can include biosolids or non-biosolids-based fertilizers. Except for the heat-treated granular biosolid fertilizers, all other were ceased to less than 2 millimeters to remove large particles such as rocks, wood, and also to get homogenized sample. 10 compost city wastes were obtained in 2017. 18 commercially available fertilizers were obtained in 2014. For the composted municipal city waste, the fertilizer 1 to 7 contains food waste and food packaging materials. The fertilizer 8 to 10 are only consistent with leaves and yard waste. We hypothesized that fertilizers containing food waste and packaging material would have higher PFAS level than those without food waste. For the commercially available fertilizers, fertilizer A through G does not contain biosolids, whereas H through R fertilizer contain biosolids. We hypothesized that fertilizer containing biosolid would have higher PFAS level than those without biosolids. And some are composted, some are heat treated, and one fertilizer is blended product. Briefly going over the experimental method, fertilizer was extracted with solvent several times, analyzed via an instrument. For the pore water measurement to estimate the leachability, fertilizer were incubated in water for 48 hours, and pore water was collected by centrifugation and analyzed for PFAS. There are more than 3,000 PFAS products are available, but due to limited analytical standards and methods, it is very difficult to estimate the total PFAS concentration. Thus, measuring only 17 PFAS can lead to underestimating the PFAS risk potential present in the environment. Total oxidizable precursor assay, which is known as TOP assay, can help estimate the concentration of unknown PFAS precursor through oxidation of precursor to PFAS. This is a brief illustration of how the TOP assay was carried out. Looking at the results, this is the results on the PFAS level in the commercially available fertilizer that were obtained in 2014. Fertilizer above the red line are non-biosolid-based fertilizers, while below the red line is biosolid-based fertilizer. You can clearly tell that biosolid-based fertilizer have much higher concentration than non-biosolid-based fertilizer. Among the biosolid-based fertilizer, long-chain PFAA such as PFOS or NP4, which is yellow, red, purple, those longer chain were more dominant than the shorter chain PFAS. Now looking at the result in PFAS level in municipal or city waste compost were obtained in 2017, and those are provided by Zero Waste Washington. Fertilizer composted with food waste and food packaging material showed much higher PFAS concentration than compost with leaves and yard waste. Among the compost with food waste contain more shorter chain PFAS than longer chain, such as PFOS and P4, which are different trend as we observed in the fertilizer obtained in 2014. This can be due to the phase out of those PFOS and P4 related products. The recent studies show the higher PFAS levels are detected in food contact material. Current FDA approves more than 90 PFAS used in food contact material. One thing to point out that P4-free food packaging is not the same as PFAS-free, and any alternative PFAS or other than P4 may be used in the P4-free food packaging. It's the same thing as BPA-free. It's not that there are BPA-free, but they use alternatives such as BPS, BPAP. So when we compost food packaging material, they would treat the PFAS as packaging material breaks down and PFAS can release to the compost. Also, food that were contact with those PFAS packaging material can also contaminate the PFAS, which also can release PFAS during composting. To see the result in one slide, I put those two graphs together. So this is showing a summary of the results. Moving into temporal variation, this is not composted biosolid fertilizer, but I wanted to show you the temporal trends of PFAS level from 2014 to 2018. From 2014 to 2018, total PFAS concentration was reduced about 50%, which was mainly due to the PFOS reduction. This is great news that the level has gone down, but keep in mind that we only analyzed for 17 PFAS and there are more than 3,000 PFAS currently available. More analysis on alternative and other PFAS level will be needed. This is the result of poor water concentration of selected PFAS. Shorter chains were more readily leached out from fertilizers compared to the long chain, which is consistent with other studies. Some of the levels were higher than the EPA advisory levels, but remember this is just biosolid water without soil, so PFAS will be diluted and attenuated by sorption depending on the application site characteristic or management, also the chain length. Top SA was used to estimate the level of potential PFAS. So x-axis are showing different type of fertilizers and y-axis are showing the total PFAS concentration in micrograms per kilogram. Black bars stand for the PFAS concentration in the extract, which is before top SA, whereas the gray bar with dots stand for the concentration after the top SA. If the gray bar is higher than the black bar, it means that fertilizer contain PFAS precursors that potentially transform to PFAS, which we couldn't measure by detecting only 17 individual PFAS. There are a few fertilizer J and Q with red shade that showed increase in total PFAS after top SA, which may result in potential increase in PFAS load during application due to the degradation of PFAS precursor to PFAS. This is a summary of the presentation. So higher PFAS concentration in the city or municipal waste compost with food waste and food packaging material had higher concentration than the other without the food waste. Also, biosolid-based fertilizer contain higher PFAS level than those non-biosolid-based fertilizer. Samples were collected in 2014, were dominated with long chain PFAS, whereas short chain PFAS were dominated samples that were sampled in 2017. The temporal trend from 2014 to 2018 were showing the decline of long chain PFAS, which resulted in the reduction in total PFAS level, but which is unsure for the alternative PFAS use, so more research are needed. Poor water concentration, some of the poor water concentration were higher than the EPA advisory level, but PFAS will be diluted when applied and attenuated depending on the application site, characteristic, management, and PFAS chain length. PFAS analysis on the municipal waste compost was used to help pass two bills by the Washington state, and it is the first state to pass the law prohibiting PFAS in food packaging material. Now, New York, Rhode Island, and San Francisco are also banning PFAS in food packaging. I hope to see more states to follow that trend. Decreasing the use of PFAS products such as food serviceware could help reduce PFAS loads in waste-derived fertilizers, as well as separating the source of compost and making careful decisions on what we compost could decrease PFAS level in our compost. More studies are needed to determine the leachability of PFAS from waste-derived fertilizers, but risk assessment should include subsequent sorption and dilution of PFAS concentration leaching from the waste-derived fertilizers. And now we'll have hearing from Rose. Thank you.
Thank you. So I'll shift gears a little bit and talk about fluorinated chemicals in compostable products, a certifier's perspective. For those of you who don't know BPI, we're a nonprofit. Our goal is scalable diversion of organic waste to composting by verifying that products and packaging will successfully break down in professionally managed composting facilities without harming the quality of that compost. You may have seen our logo. We've been certifying products for over 20 years now. The swirl is our certification mark, and then you can see we break down how our claims are made for packaging to make those claims very clear. We certify to the ASTM specifications for compostability, which are D6400 for plastics and polymer-based products, or D6868 for fiber or paper items that have a polymer component. These ASTM standards include pass-fail criteria for compostability, which includes multiple tests. So we break those into three general categories. Biodegradation, so that's the conversion of organic carbon into CO2, demonstrating it's food for microorganisms and not bioaccumulating. Disintegration, so the physical breakdown of the finished product to ensure no visual contamination, as well as a series of tests to indicate there are no adverse impacts on the ability of the compost to support plant growth. That's heavy metals limits, germination rates on plants for two different plant species. We certify to, we call it a third-party certification process, and you'll hear more about this. Ultimately, we don't set our own standards. We use the ASTM standards. The products are tested in independent labs, so we're not doing the testing ourselves. BPI staff helps coordinate that, and then we use an accredited reviewer, which is Insertco, which leads to the certified compostable product. You can find all of the products that are certified in our database online. It's publicly searchable. You can search by SKU, brand name, and if you have any issues, you can contact us. There are currently over 8,000 products listed in our database that are certified. Which leads us to the topic at hand. So fluorinated chemicals. Due to growing concerns around fluorinated chemicals, BPI had been contacted by a few composters and municipalities, as well as some non-governmental organizations about concerns. So we started participating in working groups with these entities and also hired an expert advisor to develop a path forward. As you've heard a lot about today, fluorinated chemicals are used across a number of industries, not just food service packaging, but in food service packaging, they're an effective FDA-approved grease-proofing barrier used on some paper and molded pulp food packaging. At first, we were not quite sure what our role was in this discussion. Most BPI-certified products already do not contain fluorinated chemicals. Instead, the water and grease barriers are achieved through the use of compostable biopolymers like PLA, PBAT, PBS, or PHA, as well as compostable waxes. We also sat back and thought about how, what we were being asked to do, what our role was. So BPI does not certify for all environmental attributes or for food contact. We're really certifying, as you heard in our goal and our mission statement, to make sure that the compostable products break down in professionally managed facilities and that they're not negatively impacting composters or the finished compost. And the majority of food service packaging that contains fluorinated chemicals are not items that BPI traditionally certifies. However, some BPI certified items do use fluorinated chemicals, and we started in these discussions learning more and hearing about the different aspects that really, in particular, impact composters acknowledging that this is still an emerging area, as you've heard a lot about today. We heard about how regulators were testing contact water at composting facilities, and in the case of Minnesota, where that contact water would have to be sent to a wastewater treatment plant rather than reused on site if there were elevated levels of fluorinated chemicals found. We also learned about studies showing the potential health concerns from fluorinated chemicals and the bioavailability in food crops grown in compost, and communities looking to ban products containing fluorinated chemicals. So with all of these pieces of information, and knowing that we needed to protect the trust in BPI certification for compostable products, we started to put a plan together. You've already seen quite a few slides on the levels of fluorinated chemicals in different types of compost, biosolids and food compost and yard trimmings compost. I'd like to also share some slides from the Colorado School of Mines, which you can find on the Green Science Policy Institute website. And these show specifically the uptake of fluorinated chemicals into fruit and vegetable crops. And so this was a really key piece of the puzzle for us as we considered what to do. And again, thinking about what is the impact on the quality of that compost and the bioavailability of these materials. So here it shows in lettuce and tomato crops, and also in celery and peas. And I think what's interesting to note here is, I think as was mentioned a little earlier, that the shorter chain fluorochemicals seem to be more bioavailable into the fruits and leaves and the edible parts of plants. So this definitely was one of the things that we were looking at when considering what to do with our certification. So ultimately, this all started probably at the end of 2016 and going into 2017. So at the end of last year, the BPI membership and board of directors voted to approve a 100 parts per million total fluorine limit in its certification, referencing the EN standard 13432, which is the compostability standard in Europe, to address the entire class of chemicals, followed by a statement of no intentionally added fluorinated chemicals. So what's important to note here is that, again, if you think back to the slide where I showed sort of the different elements of what we call our third-party certification, where we're using ASTM, BPI is not a standard-setting body, so we do not want to set our own standards. And so we reference the European compostability standard as that point. And we also wanted this test because it would address the entire class of chemicals rather than wading into the murky area of specific chemical compounds, since there are around 3,000 of them. And this was also part of the guidance from Green Science Policy Institute, which talks about targeting the entire class of chemicals to avoid regrettable substitutions. So the timeline is available on our website, but basically BPI certified products not meeting the 100 parts per million total fluorine requirement must be phased out of the marketplace by the end of 2019. And you may have seen a lot of news lately with some studies, a new study that came out looking at fluorinated chemicals in takeout packaging at retailers and supermarkets. Here's sort of a snapshot of that report and subsequent news stories that were sometimes quite alarming about Whole Foods packaging causing cancer. And so we historically on this topic the last year and a half have really kept our head down, but we did want to respond to that and created a press release of our own, which is on Biocycle's website, trying to clarify some of the claims of these toxic, quote-unquote toxic chemicals in compostable products. Again, assuring composters and municipalities that at least from the perspective of compostable products being a source, that this is something that is that we're quite aware of, we've been involved with for the last 2 years, and we already have a plan in place to address this, and companies are already in the process of testing and reformulating to ensure that our members' products are not a source for composters. So in conclusion, fluorinated chemicals are used in a wide variety of applications. It's not just a compostable product problem. Many of the fluorinated chemicals used today in food service packaging, they are FDA approved. It's possible that they could be coming from overseas and be in a non-FDA approved version, but most of them are FDA approved. However, due to the concerns around persistence and bioavailability in compost, this is what led BPI to proactively update its certification to restrict and then eliminate the entire class of chemicals. And I would just conclude by saying that compostable products and packaging play a pivotal role in the zero waste movement, and we're working to ensure that our certification will continue to be a trusted benchmark for compostability. And I think this goes in line with what Jeff was indicating earlier in this webinar, that we don't want this topic to derail all of the good efforts of composters and food waste and yard waste diversion programs, as well as biosolids composting. There are a lot of other benefits, as we all know, to compost, and we want to make sure that we address this concern, but not let it cause so much alarm that it derails the programs we've worked so hard to put in place. And with that, I'll pass it back to Ned.
Thank you, Rhodes. And I appreciate the idea that Rhodes brought in, which is that we are addressing these concerns proactively in the residuals management composting world, and that is appropriate. And the appropriate response really is to phase out any of these chemicals that are clearly concerns in terms of human health impacts or environmental impacts. I'll mention that it seems unlikely that there are going to be environmental impacts discovered for these. We've been using these composts and biosolids for many years around many different places and have shown significant benefits. And all those materials that have been used in the past have had PFAS chemicals and PFOA and PFOS in particular at higher levels than they are in the materials today. So there is some evidence, at least, that they're not creating environmental issues significantly. But more research is needed, and that's one of the recommendations that we have for these materials and for composting. So in summary, biosolids compost will contain PFAS in the tens of parts per billion range. Other composts may be in the single parts per billion or slightly higher range. So they are in our materials. We need to consider what that means. Some states are creating very or low drinking water, groundwater, and surface water and other standards for the most prominent PFAS, especially PFOA and PFOS at this point, because the most is known about them. And those numbers are in the tens of parts per trillion. Again, it's 3 orders of magnitude difference between what is in our compost materials and what the drinking water levels are being set at. So that's where the issue comes when there is some leaching potential from our composts. Because PFAS are persistent and can leach, there's a chance of that leaching to reach groundwater or surface water. So we need to pay attention to this issue. And now, currently, because the focus is on drinking water, several states are imposing or considering imposing drinking water enforcement levels or standards, maximum contaminant levels or MCLs. For example, in New Hampshire, there's a regulatory process started setting MCLs for 4 of the PFAS compounds. And these numbers, where these numbers end up, will potentially cause disruptions or require exemptions or something for compost use and composting site management. So here's some interim guidance. We don't know a lot. That's clear. And it's a developing topic. So and further research is needed in specific towards composting and soil behavior and such. But for now, one of the things we can say is the way things have been managed to address other leachable compounds such as nitrates, those are going to help protect against PFAS migration as well. So continue to manage composting sites for nitrate, and that will help with the PFAS as well. Continue to apply and use compost in accordance with agronomic rate. Again, The nutrients are in parts per 100, which is significantly higher levels. And if you're managing to apply just according to what is needed at a site for the agronomic use of the plants there, you're going to be restricting the amount of parts per trillion or billion that you're applying in the compost. Healthy soils can break down and sequester trace chemicals, but and that's often the case with most chemicals. But with PFOA and PFOS, they seem to be bound to soil, but the shorter chain PFAS seem to leach more easily. Maintain setbacks and buffers from water bodies, just as we've done in the past. Again, we do that for nutrient management, but if we do it for nutrient management, we will be protecting surface waters from any potential PFAS migration as well. And then consider testing your compost products, but be careful because, as Jeff noted, these chemicals are everywhere and analytical levels are challenging, especially when testing solids, and there is no approved method yet at this point for solids. Evaluate potential sources of PFAS in feedstocks. Look upstream for industries that use any of these chemicals in the feedstocks coming to your compost facility. Sample and test and consider reducing any inputs of PFAS, but be careful. Sampling and testing, as I said, is challenging, and you should consult with experts who have experience. There are some good guidance documents out there. Understand the limitations of what PFAS labs can do or lab analysis can do. It's still an evolving science. It's gotten much better in the last year or two, but it's still evolving. There's expected to be EPA approved or at least draft EPA lab validated tests coming out for PFAS in waters other than drinking water and in also in solids coming out next year. So you might start planning, but might as well hold off until those approved methods are there and the labs are using them. And then we need to communicate, of course, with employees and customers and bring them up to speed on this particular issue and the unknowns around it, and also, as Jeff said, all the benefits that are still there regarding composting and compost use. Those benefits do not go away just because of this issue, and I think our goal is to help phase these chemicals out if they need to be phased out, and then to protect the quality of our composts. And so we'll suggest, an interim guidance is to support societal efforts to reduce use of PFAS. We're also working on research proposals here at NEBA. We've had some field evaluation proposals we've had one for a while, and we're looking to perhaps help facilitate research to evaluate how significant an issue this might be for residuals management programs, composting applications, and such. Thank you very much, and I'll mention, as I do in these presentations about PFAS, that I use biosolids compost at home, and I will continue to do so. Knowing what I know, I think the benefits still far outweigh any potential risks. And I thank you for your time. Thank you to the presenters for their fine presentations. A lot of good information here. And I'll turn it back to Carrie now for questions and answers.
All right. Thanks for everyone. Great information provided. I've got some questions lined up here, but just before I do, and to catch as many of you we've had before you log off, just make sure you note that there will be a feedback form popping up when you sign out of the web page. Please take a minute to provide some feedback for us. Also, you'll have an opportunity to sign up for the Composting Collaborative. Consider joining us. You could also consider signing up for the Composting Council's newsletter on our website. We will continue to collect resources around PFAS and continue to follow up on this issue. I expect we'll have another webinar in another year or so to update everyone. So with that, I've got a few more announcements at the end, but let me hold those till we get to get up some questions here. So going back on a question about how can we tell if PFAS are present in any given product that we may be purchasing or using, or how to avoid it. Who wants to? Maybe Jeff. Do you want to try that one?
Oh boy, I really don't know. I mean, one of the things that's been challenging is the lack of EPA-approved standardized methodology, and some of the testing we've seen for composts, labs are reporting detection limits of 1 part per billion, yet we know there's some there well below that, and then the question is, what compounds are we looking at? I think as Rooney presented, we have short and we have long chain compounds. We have a variety of different PFAS compounds. I don't know how we know, quite frankly.
And this is Ned. I'll also pitch in on that, which in case the caller was thinking about consumer products that they, in our households that they're looking at, there is generally no labeling requirement. There are occasionally now products that are labeling themselves as fluorine-free or such. But the products that we use in our homes, furniture and carpets and things, often at the furniture store, they'll ask you if you want to have a stain protector applied to your furniture or things like that. Those are generally PFAS compounds, though some of them now are being, replacements are being used, non-fluorine replacements are being used. So you can ask about things like that. And then the food packaging, it's hard to know whether any particular pizza box or microwave popcorn bag or something might have traces or be using a PFAS compound. But in general, I think manufacturers are aware of this issue. It's been around for a while, and I think many are switching to either the shorter chain, likely less concerning compounds, or phasing out of the PFAS completely.
Okay, thanks. Here's another one. Rooney, you may want to take this one, but others can chime in. Have any tests been done on composts with just food residuals and yard debris? In other words, without any serviceware?
So looking at our research results and the sample analysis, we haven't had those compost with just food vegetable yard debris, but I'm assuming that food was maybe contact with those packaging material that has PFAS, maybe migrate to the food. So I would see some of the PFAS, elevated PFAS level, even though there's no food packaging material, was composted in the compost. But I haven't seen any test on just food, vegetable, or yard. I mean, the combine those two. Dr. Lee, any comments on that? Maybe not.
She may be on mute. Oh, well, let me pose another question, and then if Dr. Lee can unmute herself, we can come back to that.
Okay.
And this is related to it. So, is the higher levels of PFAS in food due to higher levels generally in food, or is the packaging in the food waste? I'm sorry, question's not quite making
probably
sense.
in the food compost, higher levels in the food compost due to higher levels generally in food or in the packaging it was in.
Right. And I think, as you just said, as Rooney just said, there's clearly some migration from the packaging into the food itself,
Right.
as opposed to it being from the food where it was grown. But as Ned mentioned, there's still not very good data in terms of plant uptake from soils or from soil water.
And there have been a couple of surveys of food products off the shelf and looking for PFAS, and it was one I know of was a while back when the detection limits were not great, but most food products aren't showing significant levels or at all. Most were non-detects in that, but occasionally you had some here and there. Go ahead, Dr. Lee.
And this is Rhodes, and I think that's a good point. And one of the things that's difficult about this topic is just that because fluorinated chemicals are used so widely across a variety of applications, including ones where they're dispersed into the environment in large quantities, for firefighting. We don't know all of the ways in which they can end up in the compost. The issues of transfer from food contact, even, I've seen conflicting information on that. Some studies show that there's very little transfer of fluorinated chemicals from the packaging to food. And I think it could be from water usage, chemicals. So it's really not clear, I think, at this point what all the potential sources are.
I agree, because I was looking at the composting site of one of the my sample, and then the site was surrounded by industry that uses PFAS. So maybe due to those industry impacts can elevate those PFAS levels as well. So I totally agree with the uncertainty with those PFAS levels, where they coming from, and what is really causing the elevated level in the compost.
This is Jeff Cooter. We know, for example, that sites around industrial manufacturers, which were making PFAS, that there was atmospheric deposition to soil. And it is likely then that in those cases, that leaves and yard waste from those sites where there's general soil contamination, are also going to contain some level of PFAS. That's why it's very difficult to say, oh, this is a biosolids problem or this is a paper product problem. This is a general environmental problem. One of the things that was intriguing in New Hampshire when they first started testing wells and drinking water sources is that some of those sites with very high levels, or levels above the EPA advisory levels, were very remote rural areas. And in some cases, the supposition was perhaps it was the floor wax being used at a school that was resulting in the contamination of the drinking well at that school. And this was a rural area. So again, these products are so widespread in consumer products that it's impossible to get to zero. And we are looking at levels pretty close to zero in these laboratory analyses. We're looking at trying to get the levels of parts per trillion. And as Ned pointed out, when we typically are looking at composts, we're looking at metals and nutrients at thousands of parts per million. If we're looking at percentages. So this is what makes this very, very challenging for the beneficial reuse and recycling of organic residuals.
Well, I am very sorry to have to say that we're out of time, because we have so many questions piled up, and I'm just I think we're just not going to be able to accomplish getting to them. I'm going to take one more, though, because I just think this is one pointed question. In terms of, if you do find, is there any method actually to treat contact water which we might think about as leachate, but really just contact water that's coming off a compost site that might have PFAS? Is there anything at this point?
At this point, we didn't. This is Ned. We didn't cover the treatment technologies. It's a whole other area, and there's been a lot of research and a lot of implementation of treatment systems for drinking water in particular. And granulated activated carbon is kind of the standard go-to at this point for treating drinking water. And there are other methods that are in development and tend to be somewhat more expensive. And they also, all of the treatment methods have to take into account the different effectiveness on different lengths of the PFAS compounds. So short chain versus long chain systems will work differently for them. So a targeted approach is needed. But in terms of treating waters other than drinking water, it's much more challenging, as you know, because a granulated activated carbon system will be blinded or bound up pretty quickly if you have a lot of dirty water going through it, and the cost then could be considerable. and these systems tend to take out other chemicals as well, other trace things. So the amount of PFAS they get in the process may not be significant enough. So this is an ongoing research on this area, and it's going to be a significant concern for some time, figuring out whether we can cost effectively treat waters other than drinking water.
Well, thanks, Ned. And I think with that, we're going to have to close off questions. Remember, we have just a quick announcement here of our next webinar for January on food waste recycling math. It's going to guide you. The webinar will guide you through how to answer questions like how much food waste are we talking about, and is there adequate processing capacity in our state or region in terms of composting and anaerobic digestion. So be sure to tune in for that. Remember, the slides will be available. You'll get a link and a note in your email with that information. You can please consider joining us at the collaborative. It's currently still free to join. We're really just trying to build our community and take advantage of all the work that is going on out there and provide a platform for exchange of ideas and collaboration, working together to solve and address the myriad of issues that we face in growing our industry. So with that, I'm going to bring this webinar to a close. Thank you, everyone, for joining us.
Thank you. Please stand by.